Good evening, all. Welcome to the Charles David Keeling Lecture. I'm Evan DeLucia, Professor of Plant Biology and Director of the Institute for Sustainability, Energy, and Environment here at the University of Illinois. The Institute, IC for short, was created to bring the best minds at the University of Illinois campus together across departmental boundaries to tackle grand challenges facing society. Our mission in IC is to leverage the enormous academic strengths on this campus to conduct interdisciplinary, actionable research addressing grand challenges in energy and environment, to help train the next generation of scientists and leaders, and to make our campus a national model for sustainability. Before I get to the Keeling Lecture tonight, I want to introduce you to IC faculty affiliate Gillen Darcy Wood, a professor of English, who is going to introduce you to an exciting new educational opportunity brought to you through IC and partner academic units. Gillen?
Thanks, Evan. So one of the missions of the Institute for Sustainability is educational, and the education of undergraduates in turning data into narrative, in taking the kind of science of environmental change and climate change that we'll be hearing about this evening and communicating it to the broader public. We feel that there are gaps in the current curriculum in this regard. So I have a flyer here, and it will be available outside at the dining tables after the event for undergraduates in the audience and others who are interested for new courses in environmental writing. You are looking at the new director of the certificate in environmental writing at the University of Illinois, the first of its kind in the United States, a three-course sequence in skills in environmental writing and communication for any offered campus-wide. You can take individual courses or the entire certificate. So turning data into narrative is our theme, and we're hoping to, we debut in the fall, and we're hoping to build a large program and profile on campus in environmental writing. Thanks, Evan, and I look forward to the lecture.
Talking about a captive audience infomercial. I think we got him there, David. Thanks, Gillen. So IC is once again pleased to be part of Illinois' Earth Week festivities, and we're excited that this lecture is one of four that we are hosting this week. And this one will be on climate change, arguably one of the greatest challenges that we've faced. I'd like to give you a little background about the Keeling Lecture. This event is named for Charles David Keeling, a 1948 graduate from the Department of Chemistry here at Illinois, who became renowned for making extremely precise measurements of concentration of carbon dioxide in the atmosphere, one of the main greenhouse gases in our atmosphere, and one that's changing quite dramatically. These measurements clearly indicate that atmospheric concentrations were increasing, leading to the recognition that human activities are having a significant impact on the Earth's climate system. After receiving his PhD from chemistry at Northwestern University in 1954, Keeling spent most of his career at the Scripps Institute for Oceanography until his death in 2005. As the first to confirm the accumulation of atmospheric CO2, the increase in atmospheric CO2, he produced a data set now widely known as the Keeling Curve. To quote Charles Kennel, former Scripps director, his measurements are the single most important environmental data set of the 20th century. Keeling also constructed one of the first models of the global carbon cycle to include anthropogenic carbon dioxide in the model, and has used that model to predict changes in CO2 concentrations in the atmosphere and aquatic and oceanic systems. His measurements also demonstrate the now well-known annual cycle of carbon dioxide that we see in the atmosphere, representing the breathing of the biosphere. Each year, IC, the School of Chemical Sciences, the School of Earth, Society and Environment, the Department of Chemistry, and the Department of Atmospheric Sciences come together to sponsor a lecture on climate change in honor of Keeling's legacy. We're very pleased to welcome a distinguished and accomplished speaker this year. Dr. John Walsh, who will be our speaker, is Professor Emeritus of the Department of Atmospheric Sciences here at Illinois. He first joined the faculty as assistant professor in meteorology in 1974, and since has conducted internationally recognized research in climate change in polar regions, Arctic sea ice, and extreme weather events at the poles. He has held positions at the National Center for Atmospheric Research, the Naval Postgraduate School, and the University of Alaska Fairbanks. From 2004 to 2013, he served as director for the National Oceanic and Atmospheric Administration's Cooperative Institute on Alaska Research. John has been a member of the Polar Research Board for more than a decade and a fellow of the American Meteorological Society since 1997. He has served for more than 20 years as associate editor of the Journal of Climate and served as the lead author of the Intergovernmental Panel on Climate Change Fourth Assessment report from the Working Group on Polar Regions. We're very excited to have him here tonight to deliver the 2017 Keeling Lecture. His title is The Arctic, Ground Zero for Climate Change. Please join me in welcoming John back to campus. And I would ask that we hold our questions to the end of the lecture. Thanks, John.
Thanks. Well, thanks, Evan, for the introduction, and I'd like to thank the organizers for inviting me back. It is great to be back in Urbana. It's nice to see green grass for the first time in several months. So, what I hope to do in this presentation is link the recent Arctic change to the work of Charles Keeling. And I'll start with this opening slide, which has an image for both. The picture on the left is a depiction of Arctic sea ice, which we'll get to in the lecture. The panel on the right is the Keeling Curve. It's the Mauna Loa carbon dioxide concentrations updated through this year. And you can see where the trend is relentless and upwards. The talk will be organized into 3 parts. I'll start with a background on recent changes in the Arctic, and I think you'll see that some of the changes are striking. Then we'll address this key question: can we relate the changes in the Arctic to the Keeling Curve? And that gets us into the attribution challenge. Then we'll finish with a look at the future for the Arctic and for the Keeling Curve. I'll start out on the summary of Arctic changes with this one. It's the basic temperature increase plot. It shows the changes in temperature, surface air temperature, over the last 55 years. It's for the Northern Hemisphere. It has the pattern, it's called polar amplification. The change is greatest in the Arctic relative to the rest of the hemisphere. The deep red shades indicate warmings of 2 to 4 degrees C. So that's roughly 4 to 7 degrees Fahrenheit warming over this period of 55 years. Most of the hemisphere has warmed, although at slower rates than the Arctic. In the bigger picture, this is a reconstruction of Arctic temperatures, summer temperatures in the Arctic, going back about 2,000 years. So this is a paleo reconstruction. It has the character of the famous hockey stick diagram. The background trend over those 2,000 years was a slow cooling due to mainly orbital forcing, solar orbital forcing. The increase over the last 100 to 150 years is striking. The red on that curve is from the instrumental measurements. The blue is the reconstruction from the proxy data, things like pollen data, sediments, ice core air bubble measurements. And you can see that in the last 100 years, the Arctic's temperature, at least in the summer season, has gone outside the range of the previous 2,000 years of variations by quite a bit. Now, temperatures have warmed by a few degrees, but over the last decade or so, Exhibit A for Arctic change has been sea ice. And this time series shows the coverage of summer sea ice, the ice that remains at the end of summer, going back to the late 1970s when satellite records began. And it's a fairly precipitous drop. There are ups and downs along the way due to year-to-year variations, but the overall change over this 35 to 40-year period has been about 40%. We've lost about 40% of the ice that survives the summer season. So that's taken as one indication of the changing Arctic environment. We'll come back to the reasons for it in part 2. Here's a spatial depiction of what this change amounts to. And this is from the website that's hosted here at the U of I. Bill Chapman from the Computer Science Department has put this website together. The two panels there show you the coverage of the summer sea ice, actually the coverage in mid-September, at about the time the ice coverage bottoms out, back in 1980 and in 2015, summer before last. And this does show you the loss of on the order of 40% of the ice cover. The main message for the climate system is there's a lot of open ocean, open water, that used to be ice covered for several summer months. So we now have coastal communities that have open water offshore rather than sea ice for several months of the year. That leaves them vulnerable to storms and other impacts. Here's a longer record of the sea ice cover. This goes back 150 years. This is about as far as we can go back from systematic measurements of ice cover. The blue graph, the blue curve, is for the ice extent at the end of March, so that's essentially the late winter ice cover. The red is that late September ice cover. And when you put this longer time horizon on the curve, the loss is about 50% in the summer between what we had back in the early 1900s and what we've seen in recent years. So the ice cover is dropping off to about half of what it used to be in late summer. It tends to reform a thin ice cover during the winter. The winter trend is much less, but that ice is vulnerable to melt, and it's lost seasonally, as the red curve shows. So this is a diagram I like because it captures this temporal perspective where we've lost 40% of the ice cover in what's comparable to one generation, at least one generation of humans. I'm not sure what penguin generations amount to in years, but the message is there. The catch with this picture is that we don't have penguins in the Arctic. We're waiting for a cartoon like this that has polar bears in it, but we haven't come across one yet. But the message comes through that ice has been lost quite dramatically, and there are impacts. I'll highlight some of the impacts here before we go on to the other variables. A lot of the coastal communities in Alaska use ice for transportation during the cold season. And there are reports across the board, North America and from the Russian side, of transportation challenges associated with the deteriorating ice cover. And that deterioration is captured here with this picture of the dog team that's not quite sure what to do as they lead their masters across the ice. Just last summer, there was a major cruise ship that transited the Northwest Passage through Canada. That deep blue line there is the track of the cruise ship. It went from the Pacific all the way around to New York through the Arctic. This would not have been possible even 10 years ago. This ship had over 1,000 passengers on it, a lot of crew members. And here's the ship being watched by the residents of a coastal community, the residents of Nome, Alaska, watching as the vessel goes by. This is one of the indications that the Arctic is opening up relative to its past history. I mentioned the impacts of storms on coastal communities. With the 2 or 3 months of open water, storms that come along are able to produce waves, flooding, and erosion of coastal communities. This is a pair of photos of one coastline, the village of Shishmaref in Alaska. And during a single storm, you can see the amount of erosion by referencing the position of the barrel along the coast. This was from just one storm. It's not unusual to lose several feet of coastline during a storm. You figure now there are several storms in a typical open water season. Accumulate that over several years, and you have a retreating coastline that's going to impact the communities. And one example of a community that's now facing a forced relocation because of the coastal erosion is this community. This is Kivalina, which is in northwestern Alaska. It's out on a barrier island. You can see how they've tried to sort of stem the tide literally with a breakwater that may hold things off for a while, but over time, this village is doomed. It's going to have to move. Move to the mainland will cost on the order of $100 million, and the question of who's going to pay for it has yet to be answered. If there were a clear funder of the move, the community would probably not be there right now. Turning to the physical side, when you open up this amount of formerly ice-covered ocean, the ice albedo temperature feedback can kick in. The darker surface, shown there on the left, absorbs a lot more solar radiation than the ice and snow-covered surface of the past. There have been evaluations of how much additional solar radiation is being absorbed and heating the upper ocean. And the trends amount to several percent per year. Over 30 or 40 years, that amounts to a doubling of the amount of absorbed solar energy in these areas that you see in red or yellow. That has an impact on climate. And here's one impact on the climate of a location at the northern edge of Alaska. This is a time history of the October temperatures at Barrow. It's the northernmost community in Alaska. And this time history goes back to the early 20th century. There are three colors of dots there. The warmest third of temperatures are red. The values in the middle third are black. The values in the coldest third are on the bottom. What's striking here is that in the last 15 years or so, every single year has been in the warm third. So this community has actually seen a climate change in the autumn. It no longer gets cold months like it used to in the past climate. So at least on the local scale, there is evidence that climate is being impacted by the loss of sea ice. And we'll take a look at the broader impacts on climate towards the end. One more cartoon. This is another one that strikes close to home. There may be impacts locally on Arctic climate, but as we say here, it hasn't quite come down to this yet. Although, I should point out, there have been reports of lightning and thunder on the tundra of northern Alaska. These reports were not in the historical record up until the last decade or so. So changes are occurring. This figure is also a gross oversimplification. No one really lives in igloos anymore in the Arctic, but I think the message is there. Climate and weather can be changing, and they can be changing in ways. The other message here is the changes in climate and weather can be in ways that people aren't prepared to adapt to. If there were a tornado bearing down on that residence, there's no lower level to go to. No interior rooms, I suppose. Moving beyond sea ice, it turns out that snow cover has also shown a fairly precipitous drop in the Arctic, at least during the spring season. There are two curves on this graph. The red one is the June snow cover going back to the late 70s. The blue line is the September sea ice extent that we looked at earlier. The scale has been changed a little differently here, but the main message is that the loss of snow cover in the spring is even greater than the loss of sea ice in September. And spring is the month when snow cover on land has its maximum leverage on the amount of absorbed solar energy. So that's a key ingredient of the energy balance for northern ecosystems. One of the other big variables of concern is permafrost. Permafrost is ground that remains frozen, at least at some level, through the year. It does not completely thaw. And that diagram on the left shows the distribution of permafrost in the Arctic. Continuous permafrost is in green. The discontinuous and more sporadic is in blue and yellow out to the pink. You can see where a large part of the Arctic is it does have permafrost, frozen ground. If you look at the measurements of ground temperatures, you find that they're warming in line with the increase in air temperatures. The measurements of the diagram on the left is for sites in North America. The diagram on the right is for sites in Canada. Across the board, there's been an increase in ground temperatures. And one location where this really strikes close to home and is a concern is in the city of Fairbanks, which has a population of about 100,000 people. This is the ground temperature at Fairbanks over the last century or so, close to a century. Right near the surface is red, a meter down is blue, the other colors are in between. That horizontal black line is the freezing line. And you can see how in the last few decades, the above freezing temperatures have started to predominate. So this means that the permafrost in that area is at risk. Here are some of the impacts of thawing permafrost. These two photos of houses are from the Fairbanks area. They're houses that are built on permafrost. The two lower photos are from Siberia. Now, one of the challenges in sorting out the effects of climate change is that as soon as you put in a building or a road, you're disturbing the ground surface and the energy balance, and there's probably going to be some thaw even if climate doesn't change. So these things may be exacerbated by climate change, but the climate is not really the only problem. There are areas, though, where you can see the effects of climate on permafrost once you get away from the infrastructure. This diagram, or the photo on the right, is something they call a drunken forest. It's one where the trees have started to tip over at different angles because they're losing their support, which used to be frozen ground, it's now thawing ground. And here's an example of thawing permafrost from the tundra in northern Alaska. This is where you can see that the changes to the landscape are major. If you have any sort of building there, it's in real trouble. There are no buildings here, so this thaw was climate-driven. And this formation of the gullies is referred to as thermokarsting. And it is one of the signs of thawing permafrost that's becoming more widespread in the northern parts of the state. Glacier retreat is accelerating. Here's a pair of photos of the same glacier. Top one is 1941. The bottom one is just a year or two ago. And you can see the retreat of that one pretty strikingly. If you put the glacier data together, you come up with some perspective on the consequences for sea level. This is an interesting bar graph in which the contributions to sea level rise have been broken out into glacier contributions, land ice contributions, and other factors. The time period spanned here is 150 years. So we're going back to the pre-industrial period. The black bar there is the contribution of thermal expansion to sea level rise. And that's in the neighborhood of a millimeter a year. The light gray is the terrestrial storage change. We've actually removed water from the terrestrial system over this time. These black and gray bars are the non-Arctic land ice contributions. The black one is Antarctic land ice, so that's the Antarctic ice sheet's contribution to sea level rise. This gray bar portion is from the tropical and mid-latitude glaciers. But everything in color is from Arctic land ice. And you can see how that's comparable to the thermal expansion effect. The purple is the Greenland ice sheet. That's the biggest contributor. But even the smaller glaciers, which are coded by region, color-coded by region, have contributed substantially to sea level rise. So this loss of Arctic land ice, glaciers, and the Greenland ice sheet is a player in the sea level rise problem, and that's one that has global impacts. The concern about Greenland is highlighted here. This is a history of Greenland's contribution, just the Greenland ice sheet, its contribution to sea level rise going back to about 1850. You can see the acceleration over time, and it's that acceleration that is the real concern. Even back in the 1800s, there was a very slow contribution to sea level from Greenland's loss of ice, but that has accelerated to a rate that's almost an order of magnitude larger than the rate back in the pre-industrial period. In fact, over this most recent decade, the contribution was 0.5 centimeter, so that's 1 centimeter of sea level every 2 decades if Greenland just continues at its present rate of ice mass loss, let alone further acceleration. So we've surveyed the changes that are going on. Now we'll come to this attribution topic. Can we relate these changes to the Keeling Curve? And here's the Arctic's version of the Keeling Curve. This is the CO2 time series for Barrow, Alaska. Evan mentioned the seasonal cycle where the biosphere breathes. In the northern land areas, there's even more biosphere to do the breathing, so there's a larger seasonal cycle. You can see how this winter's value was actually up in the 415 range. So we're certainly not tapering off in the Keeling Curve's Alaska rendition. Now, for attribution, I think the point we want to make is that this increase in CO2 even predates the Keeling Curve. The last part of each of these curves is based on instrumental measurements. The small circles that go back to 1750 are based on ice core measurements, samples from the air bubbles trapped in the ice cores. You can see how CO2 has been accelerating its increase, but even back to 1900 and beyond, there was an increase. Same for those other major greenhouse gases, methane in yellow and N2O in red. Given that more or less steady and relentless increase, it's an accelerating increase, we're faced with the challenge of explaining diagrams like this. We looked at the start at this panel. It's the temperature change in the Arctic over the past 55 years. The one on the left is the same picture drawn with data through 1975, using the last 40 years of data. In fact, when I started in research, the first paper was on Arctic temperature changes and how the Arctic was cooling. We didn't have the fancy graphics back then, but we did have the data. And that was almost famous last words. But we would like to diagnose why the change in trends over multi-decadal periods is so large if greenhouse warming, greenhouse gas concentrations are the drivers. In other words, we'd like to fit all the drivers into one consistent story that lets us attribute the changes that we're seeing to the different forcers. And to do that, I'll show results of 3 attribution studies that have used somewhat different approaches, but they all come up with about the same conclusion. The first one is summarized in this graphic. It's an excellent model study that was done a few years ago by a group in Canada. The Canadian Climate Center did this study. They used a large ensemble of model simulations to diagnose the trends in Arctic temperature over 3 time periods: early 20th century, mid-20th century, and this most recent period of warming, at least through 2005. And they took model simulations that had all forcers in there: greenhouse gases, land use changes, aerosols. The greenhouse gas bar is the set of simulations that were forced only by greenhouse gas increases. The NAT set of bars were simulations driven only by natural variations, by natural forcing, and by that they meant solar variability and volcanoes. And the bottom set of bars show what they got when they drove the models with everything else, which includes land use and aerosols. So again, the GHG is greenhouse gases in here. The observed changes are in the red symbols here. And what they came up with is a very consistent explanation for what's gone on. In the most recent 30-year period, greenhouse gases have been the driver of the warming. In fact, they've forced the system into more warming than it actually had because the other forcings, aerosols, actually had a cooling effect. In this cooling period that we just looked at with the blue and the high latitudes, the natural variability, the solar forcing and the volcanic forcing actually had a cooling effect, and so did land use, well, so did the other factors. In this case, the other factors were mainly the aerosols. They offset, or more than offset, the warming contribution from greenhouse gases. So the net effect was a cooling that's consistent with what was observed. And back in the early 20th century, there was a warming, but it was driven largely by the other factors, not greenhouse gases. So this is a nice synopsis of the evolution of Arctic temperatures in terms of the main drivers. And it is saying that we would not be seeing this warming that we've seen over the last 50 years or so if it were not for the greenhouse gas forcing. The second attribution study is this one, which dealt with sea ice and the trends of sea ice over periods of several decades. And more specifically, the authors here looked at 20-year trends of sea ice in model simulations and compared them with the trend we've actually seen over the last 20 years. The trend we've actually seen in September sea ice is about a 1.5% decrease per year. So over 20 years, that's about 30% or so. They did 3 sets of model experiments here. They did a set of simulations with what they call control forcing. That's pre-industrial forcing. That's the black. They took all 20-year segments they could get a hold of, looked at the sea ice trend, and they form a nice distribution centered on 0. There is some spread due to what's called internal variability. There's chaos in the system. So even without greenhouse gases, your trend won't always be 0. It'll be positive or negative, weakly positive or negative, but not too far from 0. The second set of experiments used what they call 20th century transient forcing. That means they used greenhouse gas concentrations and aerosols from the late 20th century. They came up with a blue distribution. This one is skewed to the left of 0. More negative trends than positive trends. Still quite a few positive trends. But none of the trends were as large as the observed value, which is given by the arrow there. The observed was that 1.5% decrease. The last set of runs was the 21st century simulation, where they used greenhouse gases projected through 2060 for this century. And they came up with a red distribution. In this case, there is still an occasional positive value. Almost all the trends were negative, and about a third of the trends were more negative than what we've observed. So what this is saying is that the greenhouse gas forcing really tilted the odds of a trend as large as we've seen. They made it certainly within the realm of possibility, maybe a third likely, although still less than the mean trend that you would get from this large sample of simulations. So the conclusion here was that, like in the previous study, we would not have gotten this trend of sea ice without the greenhouse gas forcing, but that was not the only factor at work. Last example, it's one that a study we just carried out looking at Alaska's anomalous warmth during the last couple of winters. In particular, the winter before this most recent one was extremely warm in Alaska. 3 to 6 degrees above, that's 3 to 6 degrees C above the mean. In fact, the January to April period was 6 degrees warmer than average. That's 11 degrees warmer than average for a 4-month period. And you can see how the warmth was spread around the state. These are the number of degrees above normal in degrees C. So the question we wanted to address here was, can you explain that by the wind patterns? I mean, we all know that when winds are out of the south, you get warm air. That leaves you warmer than normal. That's true here as well as in the north. The approach we used was an analog approach. We went through the historical data, found years that had the most similar wind patterns to that particular winter. The sea level pressure pattern for 2016 is colored in on the left. Here are 5 analog years which had very similar wind patterns. And we looked at how the temperatures worked out in those 5 years to see if they were as warm as the most recent winter. And what came out was this notion of excess warmth. It's the warmth that's not explained by the winds. In other words, you can't chalk the abnormal warmth up to the atmospheric circulation pattern. The excess, oops, lost it again. The excess warmth varied from 1 to 3 degrees C during the, depending on which part of the winter you looked at. It's about half of the departure from normal. So the conclusion here is that some other factor, of which greenhouse gas forcing is a prime candidate, contributed this excess warmth, which was about half of the departure from normal. We repeated that for this past winter. Turned out the past winter was almost exactly average by historical standards, but there was still an excess warmth of 2 degrees C. It's almost 4 degrees Fahrenheit, which is saying that without this extra factor, this excess warmth factor, it would have been 4 degrees Fahrenheit colder through the winter. That excess warmth factor is most likely related, almost certainly related to the greenhouse gas forcing. There are also factors like the ocean water temperatures and sea ice, which are intertwined with sea ice, with greenhouse gas concentrations. So it's really hard to get at the direct radiative contribution of the greenhouse gases to some of the other impacts that indirectly are at work. But the conclusion here, again, is that the excess warmth, the abnormal warmth, cannot be explained without something like greenhouse gas forcing. So the third part of the talk, let's see how we're on time. The future. We wanted to link the future of the Arctic to the future of the Keeling Curve. And this has been done to some extent by the IPCC. They've come up with scenarios of future greenhouse gas emissions and future trajectories of the Keeling Curve. This upper panel shows 4 future scenarios of greenhouse gas emissions, sort of a business as usual one in red, an extreme mitigation scenario in green. And that green line needs to be taken with a grain of salt because the emissions actually go negative in that scenario. It was included here to show what could happen if something extreme really did happen in terms of human activities and the handling of emissions. The CO2 concentrations that go with these emission scenarios are in the bottom panel. You can see how they shoot up to almost 1,000 parts per million in the business as usual scenario. They level off in essentially 2 of the scenarios. Those 2 scenarios are the RCP 2.6, stands for radiative concentration pathways, 2.6 watts per square meter of radiative forcing, and 4.5 in those numerical contexts. What those scenarios mean for global temperatures is summarized here. The RCP 2.6 scenario gives a leveling off of global temperatures. This is for the globe, not the Arctic. It's something like 2 degrees of warming. The business as usual, the RCP 8.5 scenario gives an increase of maybe 6 to 8 degrees. So there's a range of uncertainty there associated with internal variability and across model differences, but the curves separate. For the Arctic, which is where we want to zero in on now, there's also this separation. And you can see there's a summary here for the annual temperatures and for the winter temperatures. That winter temperature separation is the large one. You'll notice that with the sort of the non-mitigation scenario, the business as usual scenario, the warming in the Arctic winter, according to these climate models, is up above 12 degrees C. That's 20 degrees Fahrenheit, which is a huge warming. Even with the low emission scenario, in this case, we're comparing the 4.5, that's the second lowest with the red one. The warming is still 7 degrees C in the wintertime. What that means for sea ice is summarized here. For those 4 different climate scenarios, this diagram summarizes the future trajectory through about 2090 of summer sea ice. The red scenario, sea ice basically goes away in the summer. There are some reasons to think this could be delaying the loss of sea ice beyond what the real world is going to give us. If you extrapolate the present trend, you come out with an ice-free Arctic in September by about mid-century, perhaps even sooner. The other point to notice is that in the blue and the green and to a lesser extent the red scenarios, the low emission ones, sea ice does level off. It would take something like that low emission scenario, that 2.6 scenario, to level off the loss of sea ice to sort of put it under arrest at anywhere close to the present amount. Permafrost is another variable that is very scenario dependent. This is the result of a simulation for two different time slices under one scenario. It's actually the middle of the road scenario. And the red areas are areas that are above freezing. So this was the most recent complete decade on the top. You see where there are pockets of above freezing, especially in that discontinuous permafrost zone. But by mid-century, it's only 40 years from now, the reds start to dominate 2/3 of the state under that mid-range scenario. And this is a synopsis from the available climate models of how the fate of permafrost depends on the emission scenario. There are two plots here, one for that low emission scenario, the 2.6. There were 10 models that had soil output for that scenario. The high emission scenario is the one on the right, and what they've plotted in color is the number of models that had sustainable permafrost in 2099. In the low emission scenario, 10 out of the 10 models kept the permafrost over a fairly large area. There's still a loss, especially in Alaska. Most of the permafrost is gone, but over Asia, the permafrost survives under that scenario. Under the higher emission scenario, the 8.5, the number of models with sustainable permafrost is only 2 or 3 or 4 out of 15, which means that the permafrost is essentially doomed under that scenario using these climate models. So this is another example of how the scenario we follow makes a big difference. Now I'll finish up with showing the scenario dependence of several Arctic variables or several variables that are affected by the Arctic but have global implications, starting with sea level. And we'll also look at feedbacks to greenhouse warming with the Arctic involved and effects on weather and climate. This is the sea ice figure, it's the sea level figure, and it's showing the difference in various contributions to sea level rise between two emission scenarios, the high emission and this low to medium emission scenario, 8.5 and 4.5. And on the scale on the left there is the difference in sea level rise that results from the choice of scenario, the difference in scenario between these two. So it's same color coding as that diagram we looked at earlier. Thermal expansion is still the bigger factor, but the difference in the thermal expansion between these two scenarios is about 1/10 of a meter, 10 centimeters. The Antarctic sea ice and other contributions is the grays. The Arctic contributions, the Arctic land ice contributions are in the colors, with Greenland again being the purple. And the message here is that in total, the Arctic contribution to sea level rise, the Arctic land ice contribution, will differ by about 7 centimeters, 0.05 meters, depending on which scenario we follow, according to that study. Here's one plot showing the difference in projected methane emissions under two different scenarios, the same two as in the last diagram, 4.5 and 8.5. They're plotting methane emissions from lakes in black and from the land areas in red. The main message here is that the emission rates of methane depend strongly on the scenario. The upper curve's the high emission scenario, the dashed dotted curve is the low emission scenario. Both those scenarios say methane is poised to increase in its emission rates from Arctic land areas. This is based on a fairly crude model, but at least it's an indication that we should look perhaps more closely at what's in store for methane emissions from Arctic land areas with the scenario dependence sort of front and center. One other methane point is that there's permafrost below the ocean in the shelf seas. The Siberian and Alaskan coasts have some shallow shelf seas, and there's permafrost that formed during the last glacial period. Below that are some large methane stores. There's quite a bit of concern that if there's permafrost thaw in these subsea areas, there could be breaks in that barrier and releases of methane. There's a lot of debate about just how imminent this permafrost thaw and methane release is, but it is out there as an area that's being investigated. Last couple of slides are on the potential effects of Arctic change, or the potential relation between Arctic change and extreme weather in middle latitudes. This has been a hot topic in research over the last few years. Again, there's controversy on the extent of the Arctic's relation to mid-latitude weather, but the essence of the physical argument is that as the Arctic warms more than mid-latitudes, this polar amplification, you're reducing the tropical to pole temperature gradient, and that can impact the jet stream, since that thermal gradient is what drives the upper level winds. And there are two arguments for increasing amplitude of the waves in the jet stream. These are the waves that affect our weather. One is that higher pressures aloft will reduce the west to east wind speeds. The other is that with more warming in high latitudes, you amplify, or you affect the ridges, these features in the north more than in the south, and together that amplifies the wave. There's been some tantalizing work on this, but again, no smoking gun that would let us make the link. But here's one of those tantalizing pieces. It's an attempt by Judah Cohen to link major weather events of a recent winter, major severe winter events, to changes in the geopotential heights, or the pressures in the Arctic. So the reds indicate higher pressures in the Arctic. The coordinate on the y-axis is pressure, and time through the winter is on the left. And what seemed to be showing up there is a tendency for these severe weather events to occur when there was a warming and a raising of the pressures in the Arctic. There have been other studies that show this might not be as systematic. In fact, it probably is not as systematic as that figure implies, but there may be something there, and as Arctic warming continues, I'm sure that this is a research area you'll be hearing more about. So to finish up, here's the conclusion. 3 main points: the Arctic's warming, and the recent changes in ice and snow, at least those 2 variables, are unprecedented in the historical record. And depending on your time frame for temperature, you could make that same statement about temperature. Internal variability and other drivers have played some role in the recent warming, but the rate of change that we're seeing in these variables and in temperature cannot be explained without anthropogenic forcing. And that's saying that the Keeling Curve's impact is showing itself in the Arctic. We've made the link there. And the final point is that depending on human actions, depending on which scenario we follow in the greenhouse gas emission arena, the Arctic's future can range anywhere from a stabilized climate, where sea ice and permafrost stabilize, as we saw in that last section, that can range all the way up to the scenario where there's an acceleration of the change, which is more like what we've seen in the last few decades. So the message from the last bullet is that the choice is ours to some extent. So that would be the Earth Week message that we'll close with. So I'll stop there and take any questions. Thanks.
Thank you, John, for a very sobering and incredibly an insightful presentation. John would be happy to take some questions from the audience.
It's a very interesting talk. It's only in the last handful of months that I learned that there must be 15 stations that measure the CO2 concentration. And indeed, had you shown the South Pole one, there wouldn't be an oscillation at all. So I'm looking at this gorgeous data, And I'm wondering if anyone has actually tried to account for it. In principle, if I knew all the plant life in the earth and how much it grows and how much it dies back, I should be able, and I knew everything I needed to know about the weather, I should be able to calculate that. Has anyone tried to account for the wiggles and the variation with latitude quantitatively?
Well, in terms of the seasonal cycle and the latitudinal variations, I think the carbon budget reconstructions have gone a long way towards reproducing what we see in terms of the seasonal cycle and the latitudinal dependence. In terms of the seasonal cycle, if you could account for all the sources and sinks, you could do what they say is close the budget exactly. You could reproduce the seasonal cycle. The latitudinal dependence, and in fact the seasonal cycle at all latitudes, will depend on the transports by the atmosphere and the ocean between different latitude bands. So I think that's a more challenging topic. But I'm not a carbon cycle expert myself, but from what I've read, the budget reconstructions have gone a long way towards a closed budget. They certainly can explain qualitatively why we see the seasonal cycle. That's largely the vegetative part of the system. Getting it down to the exact magnitude in terms of parts per million in the amplitude of that seasonal cycle, I think is, again, the tougher challenge, but I think we're reasonably on our way to explaining it. There are also Earth system models that include carbon cycles and carbon budgets, and they can reproduce to a fair extent the seasonal cycle and the latitudinal distribution. So to the extent that these models capture our understanding, I think we are at the point where we essentially know what's going on, but we can't reproduce every detail down to the nearest part per million.
Hi. I'm right here. Hi.
Okay.
Yeah. I've seen serious writers, meaning people with credentials, say that the rate of sea level rise has not changed for decades. True, false? Could you comment on that?
Well, some of these sea level histories are based on tide gauge data, and they're also based on satellite data. So if what they're saying is true, the tide gauges are lying. Satellites are also lying because sea level has been rising.
No, the rate has not changed.
Rate.
Yes.
Okay.
Sea level's right, but that the rate has not changed, and that is if you like, a contradiction to climate change models.
Yeah. The sea level curves I've seen have a concave character, concave upwards, which indicates an acceleration. Maybe Don Wubbles could comment on that since he's worked on the assessment with the sea level people. What's the current thinking there, Don?
Both the tidal gauges and the satellite data show a clear acceleration since 1993. And further acceleration certainly expected in the future. It's very clear that there's been an acceleration.
Yeah, it'd be nice to get one of those plots, and I think you would see it concave upwards.
It sounds like we have to get your serious writers together with our serious writers to look at the same data set.
I've seen articles, and I'm sure you have too, of these giant holes in the ground in Siberia that they assume are from these big methane bubbles that are coming out of the ground. Do you agree that's what it is? And is there a concern that that's going to occur too in the North American Arctic? And have you seen any numbers of how much methane is released from those bubbles?
Yeah, I've actually talked with some people about that. And the ground ice experts aren't so sure about that methane source. Another possibility is there could have been a great big ice wedge or a subsurface pool of water that drained and took the upper part of the soil with it. So I think methane releases would be one candidate, but I don't think the final word is in on that one. Yes.
Yes, I think I'd like to follow up a bit on the methane. I've read from time to time the potential of it. the release of methane from beneath the permafrost could be a real significant player in terms of accelerating the rate of the amount of greenhouse gases and temperature. Working in the Arctic for many years, would you sort of give us your feeling or your understanding of the potential for that being a major contributor to exacerbating the problem?
Well, I mean, the potential is there. I mean, I wouldn't argue with that one at all. I think that the real question is when and how much. And if you look at that graph of the methane releases towards the end there, where the red curves suddenly jumped up, what struck me was that they're very flat up until the present, which means that we really haven't detected major increases in methane just yet. Now, that's not saying it won't happen. It's acknowledging that the stores of methane are there, but just what it's going to take to trigger it is a little less clear. And whether it really starts to spike up in the next decade, 50 years or 100 years, I don't think we're prepared to say. But I mean, the potential is clearly there. If you look at the carbon in the soil, I mean, there are huge amounts there that would amount to a major feedback on climate change if and when they are released.
Yeah, John, I was wondering, is there the rapid increase or rapid change in the rate of sea ice loss, are there models suggesting any rapid changes in deep ocean current trends that might accompany that over the next few decades? Is that also taken into account by some of these studies you're looking at?
Well, the IPCC's tried to distill the model simulations in these future climate runs. And I think that the consensus of the models is that we are likely to see some weakening of the thermohaline, the deep ocean circulation, but not a collapse, not the day after tomorrow type thing. But the body of the model output does point towards weakening rather than strengthening. That's a really tough quantity to monitor too, because you've got to have instruments in the ocean at sufficient resolution to capture the north-south transport to see if the deep ocean really is changing. And there's a lot of debate about just how much change has actually occurred in that deep ocean circulation.
Hello. Yeah. So I was curious about the models, with the RCP values, where it was 2.6 and 8 point something. I might have missed it, but could you explain what the current value of? I'm not too educated on all of this stuff, but could you explain what the current value is, and basically, how can we? What changes can we do as a human civilization to bring it to 2.6 or lower? I'm just curious from a practical standpoint what that would mean.
Okay. Well, the numbers there refer to how many extra watts per square meter of radiative energy are coming down because of greenhouse gases and other anthropogenic factors. So 8.5 means about 3 or 4 times as much of an impact on the downwelling radiative change as the 2.6. And we're tracking most closely that 8.5 scenario right now. The 2.6 is an extreme mitigation one. It's saying that we'd have to not only stop emitting carbon, but begin uptaking it so that the emissions go negative. There'd have to be a net uptake. And for that reason, some assessment studies don't even include that scenario just because it's so unlikely to happen, barring some nuclear war or whatever could be a much more serious concern than climate change. So I think the concern is that we are tracking that 8.5 scenario, which is the higher part of the envelopes that we were looking at.
Okay, hi, John. The talk that was given here yesterday by Catherine Hayhoe talked about a survey of many of the climate change studies that showed a tendency for scientists to not show the worst case scenarios. I was kind of struck by the fact that on one of the slides you showed that the September ice is lower than you would expect with emissions from the 20th century, that we're losing ice more rapidly. With your experience, have you seen a tendency for scientists to try to be conservative on the Arctic impacts?
By conservative, you mean minimizing the impacts, or say
not minimizing, but
the,
not choosing the worst case scenarios?
If anything, I'd go the other way. I'd say there are scientists who lean towards the more extreme end of the likely changes. That's the old debate. Well, you hear criticisms from the politicians about scientists crying wolf and waving the flag for their own work. It does get more attention if you cite the more extreme scenarios. But I think on balance we are. I think on balance we're balanced. But I think there are at least as many examples I've seen of people going towards the more extreme rather than the less extreme.
With that, let's thank John again for a fantastic lecture.